Dear students, this session we discuss about electrostatic potential energy for collection of point charges. That means the determination of total electrostatic potential energy for a particular system. See a unit positive charge bringing from infinite to that point O. There is no another charge. There is no charge. Now we bringing the charge from infinite to that point 1, that is Q1. The Q1 charge is bringing infinite to that point O. So here there is no charge, there is no electric field, there is no electrostatic force. So we don't lose the energy. We do only the positive charges bringing from infinite to that point O. Then we placed Q1. We find the electrostatic potential at point M due to this charge Q1. So when we place that point O, it has some electrostatic potential energy provided that point M at the distance of R. You know very well that work is equal to electric potential. That means the electric potential at any point like M at the distance of R from charge Q1 is V equal to 1 by 4 pi epsilon naught Q1 by R. You know very well in previous classes. Now the charge Q1 is already kept there, that point O. Now the charge Q2 brought from infinite to that point M at the distance of R from charge Q1. Now we must done the work. Against electric field by the charge Q1. So that work done is equal to product of charge Q2 and the electric potential at point M due to charge Q1. That is W is equal to Q2V. So that means W is equal to Q2. You know very well the V, that means the electric potential at point. That means 1 by 4 pi epsilon naught Q1 divided by Q1 divided by R. That is U is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R. So that is the electrostatic potential energy of this system. That means the electrostatic potential energy of the system for the two charges Q1 and Q2 separated by the distance R. See this equation. U is equal to 1 by 4 pi epsilon Q1 Q2 by R. That means this electrostatic potential energy of the system of charge Q1 and Q2 depends only the distance R between the two charges. So very important. So the electrostatic potential energy depends only the distance between the charges. This is the electrostatic potential energy of any system. Okay, very simple. Then we discuss we learn the another example. See this diagram. It's a system. Now we determine the total electrostatic potential energy of this system. Okay, so we follow a particular way or by this way. That means we bringing the charges Q1 and Q2, Q3 one by one and arrange them and assemble according to the configuration, that is Q1 and Q2 and Q3. You know very well, that means electrostatic potential U is equal to 1 by 4 pi epsilon Q1 Q2 by R. So see the first the Q1 charge bringing from infinite to that point A. At the time there is no charge Q2 Q3, we bringing only the charge Q1 is placed at point A. So infinite That means there is no any other charges near to point A. So there is no electric field, there is no electrostatic force, so we don't lose the energy. So that is work done is equal to 0. Then the electrostatic potential energy at point A is equal to 0. That the electric potential is that. Okay. So the charge is placed at A. Now we bringing the charge Q2 from infinite to that point B at the distance of R12 from point A or charge Q1. So now the electric potential at point B due to charge Q1, that is V1B, that is V1B is equal to 1 by 4 pi epsilon naught Q1 divided by R12 is formed. So now we do the work. Or we must be done the work, that is charge Q2 bringing from infinite to that point B. That work done is equal to product of charge Q2 and the electric potential at point B due to charge Q1, that is V1B. So the work done at point B is equal to the product of charge Q2 and the electric potential at point B, V1B. That is, this work converted or stored as a electrostatic potential energy at point B. Then another charge Q3 also bringing the charge Q3 bringing from infinite to that point C. So here when the charge is placed at point C, so the two potentials are formed because of the two charges are there. So the potential at point C due to charge Q1, that is V1C. V1C is equal to 1 by 4 pi epsilon naught Q1 by the distance R13. Then also the charge Q2 produced a electric potential at C, that is V2C. So that V2C is equal to 1 by 4 pi epsilon naught R23. Okay. So now we done the work. We must be done the work against the sum of the electric field, like due to Q1 and Q2, and also the two electrostatic forces due to charge Q1 and Q2 at point C. So that work done is equal to the product of charge Q3 and sum of the electric potential at point C, like V1C and V2C respectively due to charge Q1 and Q2. That is WC is equal to Q3 V1C plus V2C. This work is stored as a electrostatic potential energy at point C, that is UC. So now we find the total energy of this system. Just we adding the potential energy like UA and UB and UC. So the three energies are added, then we get the total electrostatic potential energy of this system. Again I explain. See that at point A, there is no work done because of we bringing the charge. When we bring the charge at point A, there is no any other charges vicinity of charge Q1. So that work is 0. That is electrostatic potential energy also 0. WA is equal to 0. UA is equal to 0. But at point B, when we put the charge Q1, then it produced the electric field. So also we bringing the charge at point B. So we do some work against the electric field due to charge Q1. So that is that work is equal to the product of charge Q2 and the electric potential at point B due to charge Q2. That is WB is equal to Q2 V into 1B. So WB is equal to Q2. That is the value of 1B, 1 by 4 pi epsilon Q1 R12. So finally this work done stored as electrostatic potential energy at point B, that is UB is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. This is equation 2. Same as at point C. So at point C we do we done the work against the two electric field and also two electrostatic forces. So that's mean the two electric potential like V1C and V2C acting at point C. So that work done at C is equal to the product of charge Q3 and the sum of the electric potential due to charge Q1 and Q2 like V1C plus V2C. So Q3, you know the value of V1C 1 by 4 pi epsilon Q1 R13 plus V2C 1 by 4 pi epsilon Q2 divided by R23. So that is Q3 is multiple with them. So 1 by 4 pi epsilon R Q1 Q3 divided by R13 plus 1 by 4 pi epsilon Q2 Q3 by R23. This is equation 3. So now we need or we determine the electrostatic potential energy of this system. So just you add the 3 energy at 3, that means adding equation 1, 2, 3, we get the net electrostatic potential energy for the system. So U is equal to UA plus UB plus UC, UA is equal to 0 because there is no work. Then UB 1 by 4 pi epsilon Q1 Q2 by R12 plus 1 by 4 pi epsilon Q1 Q3 by R13 UZ value. So 1 by 4 pi epsilon Q2 Q3 by R23. So in common factor, that's mean 1 by 4 pi epsilon taking out, then Q1 Q2 divided by R12 plus Q1 Q3 divided by R13 plus Q2 Q3 divided by R23. So this is the total electrostatic potential energy of the system of charges Q1 and Q2 Q3. So this is the total electrostatic potential energy. So this electrostatic potential energy of the system is equal to the work done, that means the external work done assemble the charges, the work done to assemble the charge configuration. So this is the work electrostatic potential energy equal to work done. So we learn or we conclude from this topic or from this explanation. So we conclude the electrostatic potential energy depends only the distance between the charges, and moreover we bringing the charges in any order, the total electrostatic potential energy of the system is same. Okay, that's